So I'll be talking today about how tech is used for seabird conservation in Scotland, giving examples of two projects I've been working on recently, both of which have been in the local area or also in the coastline. So here we go. So I've worked on two very different but connected projects. One looking at gannets in the wake of avian influenza, and another looking at puffins and their borers and how we can monitor that. But both these projects started with the same question: was how we can use tools such as AI, geospatial data, remote sensing, machine learning to make monitoring and reporting easier for ecologists in light of our rapidly changing climates. So I'll show you how these ideas come to life and why digital ecology is such an exciting thing to be bringing into seabird conservation in that space. So just a little bit about the company. We are a geospatial software company. We're just 5 years old. Fully remote, so half of us are in Glasgow, half of us are in Edinburgh. And we bring together mapping, data analytics, AI, to turn data into information that's used by policymakers, decision makers, and bring them the front line of conservation to make informed decisions. So we have a web mapping platform that we call VIA that we integrate a lot of data sets into that people can then use. And the point is that they can make geospatial-based decisions accessibly without the need for a technical team behind it. So you don't need those expertise, so you can just do it yourself. My partners for both of these projects are Caroline Nicholl and Tom Reid at the University of Edinburgh's School of Geosciences. They have decades of experience in environmental monitoring, and more recently in seabird population studies. But what makes them unique is that they have an in-house facility full of a fleet of drones and light aircraft and instrumentation that's used for remote sensing and observation purposes. So it's been a great opportunity to be working with these people with this amazing technical expertise at our disposal. So in recent years, aerial vehicles and drones in particular have become a game changer for wildlife conservation because they have the ability to respond quickly to change, to reach remote or inaccessible areas, or to cover large areas in a relatively short amount of time in a really efficient way. And that makes them ideal for ecological monitoring. But what really expands their potential is their ability to carry an array of different instrumentation. So some applications of this are things like measuring or doing chemical analysis of the ejecta from whales' blowholes, and that's a sentence I don't say very often. Well, that's called the snotbot, which I think is brilliant. Or we have organisations that use thermal infrared cameras to look for polar bear dens in the Arctic. And we have organisations that use drones to locate penguin colonies in the Falkland Islands and the South Islands that I've never seen before. So as you might know with seabirds, their challenge is that they have this really annoying habit of nesting in really awkward places, making life difficult for everybody. So it's only these huge colonies in rugged terrain, could be on sea stacks out in the sea. And this is where aerial surveys and drones and light aircraft are really helping with this ecological monitoring. So the first project is focused on gannets, and this is a project I did in my master's dissertation at Edinburgh University. So it's a bit verbose, I apologise, but it's quantifying the effect of avian influenza on the northern gannet colony of Bass Rock using high-resolution drone imagery and deep learning. Now, literally all that boils down to is count the birdies. That's literally just what I'm doing, is I'm taking aerial imagery and I'm looking for gannets in pictures and doing population counts for the annual census. And this is done in conjunction with UK CEH and the Scottish Seabird Centre down the road. So Scotland, as you probably know, is a bit of a stronghold for seabird populations, and Scotland is home to 58% of the global population of northern gannets. And right here in Firth of Forth, we've got a really special place called the Bass Rock, which is a triple SI, and is or was home to the largest single colony of northern gannets in the world. That's a bit of contention now post-bird flu, but at their peak, there's more than 150,000 individual birds nesting on Bass Rock on any given year. It's an astonishing sight if you see it, and it's a great reminder of how globally important these colonies are. We're really lucky to have these in Scotland as well. So the issue we came across is bird flu, and obviously bird flu is not a good thing. So between November 21 and July 23, you might remember, there was this huge epidemic, and there was a record number of cases across the UK in both wild and captive birds, resulting in the deaths of tens of thousands of individuals across 65 different species, with a huge impact on aquatic birds in particular. Now, the disease is spread between birds through fluids, so saliva, droppings. So you can imagine that in a colony as compact as that, that's going to just run right through it. And indeed, that is what happens, sadly. So it was detected on Bash Rock in June 2022. So this image was taken by Edinburgh University in 2020, showing a thriving population. But just 2 years later, peaked the epidemic. That's the difference we have in the colony. And in fact, even, a lot of the pictures, a lot of the birds you see in that picture are probably actually dead as well. So absolutely decimated that particular colony, showing how devastating its impact can be. So this is where our digital tools start in. So traditionally, seabird surveys involve the counting of individuals. So for many years, the Bash Rock survey was carried out by taking a light aircraft and a digital camera, a film camera before that, leaning out the plane window, taking a photograph, going back home, jetting it onto your wall, and getting a marker pen going 1, 2, 3, 4. 150,000 birds, remember, so that's quite a lot of time spent just marking off birds. So clearly that's very time consuming, but as the size of the colony and the data set grows, that becomes more prone to human error. Because we are humans, you get bored, you get tired, it's a repetitive task, you have a life, there's scheduling things going on as well around that. But it means a single count can take between weeks and months to complete. So it means that when something dramatic happens, like an epidemic, it's really slow to get that immediate impact back and realise that you can then take action. And again, this is where these digital tools make a huge difference. So this project was about assessing the scale of loss in the gannet colony by counting the number of live and dead birds from drone imagery using something called deep learning that I'll explain in a second. So it's basically getting a model to predict what's alive and what's a dead bird. So I was going to compare the accuracy and efficiency of the AI detections versus the manual count done by the experts. And then compare the 22 and 23 survey data set to see how the colonies recovered after that horrendous year of bird flu. So the best replacement for manual counting is something called machine learning. So if you imagine teaching a dog to fetch a ball, you have a ball, throw the ball, dog runs after the ball, brings it back, you give it a treat to say well done, you do it again, repeat the process, the dog simply goes, hang on, I'm noticing a pattern here. When they hold the ball, it means that they're going to throw it, so I'll be ready. And then if I bring it back, I'll get a treat and I'll get a reward. Great. So the dog does this, and eventually it learns from the pattern that it's going to get a reward, so it continues to do it better and better each time. And that's a bit like what a computer does in this instance. So you give it lots of examples of a picture, it learns those patterns from the data, and then it can then recognise when you feed it a new one what it is. So if you give it tens of thousands of photos of cats and dogs, and then reward it every time it makes a guess whether it's seeing a cat or a dog, it'll get more and more accurate each time. So it learns to recognise, well, those ears are more pointy, so that's probably a cat. That's also longer, so probably a dog. And every time it gets it correct, give it a little reward, and it'll get more accurate, and then tell you immediately it's cat or dog this time, give it a person. So deep learning is a slightly more complex version of this. It's better at handling complex, messy big data like images, video, text, and sound. So it uses something called neural network, which is very loosely based on how neurons work and really how neurons to make decisions. So for recognizing an image, it does it in an incremental way. So as you see the diagram at the bottom there, it might first, if you feed it a picture of a face, it might pick out straight edges first. It might then, in the next layer, pick out curves and things. Arcs. Then the next time, it'll pick out curves and arcs and edges together and start putting them together until it eventually creates something that vaguely looks like a face. Then you go, good job, little computer, pat it on the head, give it a reward, it reiterates the process. And every time it does this process, it gets closer and closer to recognizing what a face should actually look like. So then when you give it a face it's never seen before, it goes, That's a human woman face. You go, correct, good stuff. So this is what I use to make it recognize what a gannet looked like in the imagery. So we flew a drone over Rock in June 2022 and took 178 overlapping images. These were then stitched together into what you call an orthomosaic, which is a really high resolution georeference image, which means you know the exact geographic coordinates of every pixel in that picture. This map was then split into 3,000 of these small tiles, mostly because I was going to have to count these things, so that's just going to make it a little bit easier on my eyes and my brain, so that's no other reason why I was that number. And then the first thing you do is get rid of rubbish data, so anything that either has no data in it, so it's just black, anything distorted, there's missing data there, there's distortion between the rock edge and the sea, or if it's just pure ocean and there's nothing, there's no birds in it, so I've got rid of them. So looking for good examples, so the birds are quite clear, you can see man-made structures, the edge between the rock and the ocean is nice and sharp and crisp. So that left me about 1,500 out of those initial 3,000 tiles to work with. So to train the model, say how to teach it what a gannet looks like. So there's three what we call classes in this instance. We have live gannets, dead gannets, and flying gannets. And this gives the computer a really good visual cue as to what to look for in distinguishing these three things. Luckily, these three things have very different shapes. And as we saw, our deep learning model likes to learn things based on the shape. So live gannets are very sort of oval in shape. The wings are tucked in, they might have some strong shadows around them. The dead gannets have their neck and their wings splayed out in what I call a cross chicken position. And then we have the flying gannets, which are looking larger because they're close to the drone camera. Obviously nice, straight wings, straight neck. So the computer then recognizes how to tell the difference between these three different ones. So I eventually labeled 7,000 different birds as either live, dead, or flying, quite slightly mental, but we got through it. Some of this is kept to train the model, and you keep a little bit to one side to then validate the model to make sure it's doing what you expect it to do. And then it brings out an output with its predictions. So there's 4 different colour boxes. There's pink boxes, which are the ones that I labelled as live, dead, or flying. The blue boxes are the ones that the computer has picked out, saying, I think that's a live gannet. Yellow is a flying gannet, and red is a dead gannet. So on first glance, you think the computer's done a pretty decent job of picking out the difference between those 3 types of gannet. And then it tops them up and spits out them. So it might be, 1,500 dead gannets, for example, it'll tell you that number. In an ideal world, these boxes would perfectly overlap and have the correct label on them, but that doesn't happen in reality. So the next thing is to validate that. So I went in and manually validated whether it got all these predictions correct or not. Some of them have what we call false positives. So for example, there's birds that I missed that the computer picked up, so I was like, well done. Sometimes the computer would highlight a rock as being a live gannet. And you can forgive me for doing that because if you've got a round white boulder, again, shape colour-wise, it's a little similar to a live gannet. So basically, I went through and just adjusted the numbers for that and had an adjustment factor for putting through the new data. So the results of that was that the AI detected just over 18,000 live gannets and just over 3,500 dead gannets in the 2022 data. The manual count, which is done by 3 experts in an average taken, was not that much more, so 21,000 and then versus 4,000 dead. And similarly for 2023, 48,500 live, 43 dead by the AI model, 51,000 live and 23 dead from manual count. So the good news is, between 22 and 23, that marked a 166% increase in the size of the gannet colony after the flu, which is a remarkable recovery in just 1 year. From what I understand, that number was settled at that. It's not really increasing on about 50,000. So it's probably never going to get back to 150,000, but it's stable, which is what we got after the flu. The model predictions versus the manual count was about 95% accurate, which is great for a first pass and really reassuring. But the most incredible thing about this is the time-saving quality. So as I said, it could take 2 to 3 months to get the manual count back in the wake of such an epidemic. This computer model gave me that number with 95% accuracy in literally 2 minutes. So a huge difference, and as you can see, pretty groundbreaking for these instant rapid responses that you need in the wake of incident bird flu. So this is what got me excited with what sort of digital tools can do and how you can improve these processes for ecological monitoring. So by combining drone imagery, machine learning, geospatial tools, we can go from these slower, more manual processes to something really rapid and scalable solutions over a much wider scale. But of course, gannets aren't the only seabirds facing challenges. Unfortunately, most of them are, which is then how we segue into puffins. So yes, also vulnerable to extinction, so monitoring them is also crucial. But they are one of the hardest seabirds to count because they do make their nests underground in burrows. So it means that we can't apply the exact same technology to the gannets because half of them are going to be underground at any one time, so you can't just do a count from the air. There's also a problem with there's a lack of standardization how population data is collated and stored and shared between organizations. And clearly they've got the same issues of nesting in remote colonies up on sea sites and as well. So the traditional counting methods is that one in the middle, and although hilarious, it's not the most efficient, it's invasive, it's slow, it's labor intensive. And the Isle of May alone has 40,000 burrows. That's an awful lot of holes that stick your hand out. That's a lot of pecking. But the issue for both these projects is simply too many birds and not enough time, right, to do all this. There's 500 puffin colonies across the UK, you can't do this for all of them. And with this particular method, a reactive survey likely would be the bird flu gas is really possible. So my company last year took part in what we call a CivTech challenge. So CivTech is a Scottish Government initiative, it's like a technology accelerator program, where every year they bring together the government, public sector, private sector, to solve real world problems. So organisations present a problem and you're invited to come and co-design a solution for that problem. So we were working with the National Trust of Scotland and Nature Scott directly to come up with a way of estimating how many breeding puffins there are in a given colony by looking for apparently occupied burrows, or AOPs, which is the metric used by ecologists to count puffins, but also to decrease the time, cost, and effort it currently takes to carry out colony surveys, so they can be carried out more regularly and on a much wider scale. Places like St Kilda might really get a colony census once every 10 years because of its ordered locations. We just really want to lessen that time because, like I say, these changes are happening over scales of 1 to 5 years, now, whereas before it might be 10 to 20 years. So there's a little video just demonstrating. So this, at the end of the accelerator, this is our sort of base platform that we came up with. It's going to look a little bit different from this now, but this gives you a little bit of a flavour for what we've done. Find the play button. Right, so the platform gives the element. And you collect that high resolution imaging from the drones we showed before. This is the ortho mosaic image, the 2-dimensional top-down view. So you can scroll in, zoom around, see what the words are in that top-down 2 dimensions. Then from that, we make what we call a 3D digital twin. So it's a high-resolution, interactive 3D model of the colony. So it's almost like you're standing on the ground, you can see the exact view and you can see exactly how the birds are laid out. Ecologists can then label birds as apparently occupied, unoccupied, or maybe there's a different species living in it, like rabbit, so they can log that. Their colleagues can validate that as well. And we're looking at, or we are developing AI tools that will automatically pick out where the birds are and whether they're occupied or not, as well as similarly to what with the gannets. So that will help ecologists save more time in picking out those occupied burrows. That's really important for their census counts. So I always quick to stress that this is never going to be a replacement for ecologists. This works in conjunction with ecologists. So they're going to always act as our ground truthing or validation. This just saves their time. So if they know where their currently occupied burrows are, they know that they can just go straight to that area without having to traps around really delicate habitats. They can double check that there's a topic within the burrow that the AI thinks there is, say yes there is, update the model becomes more accurate as time goes on. So eventually this will save the ecologists a lot of time when doing their census counts every year. It's what we call a virtual fieldwork platform, and basically it will save a lot of time and a lot of money to promote these remote sites, make it scalable, cover more colonies in a year, and just massively improve on the current methods. I'll just skip that in the interest of time. So what we're looking for is evidence of gardening outside of the puffin burrows. So when they're getting ready to nest, they clear the entrance of the burrow now. So you get a lot of fair hair or cut vegetation and dare I say puffin hair at the entrance. So these are the key indicators of occupancy that we have for the burrows, and it's what the ecologists best have to go on at the minute as well. So we're looking at how we can recognise that from drone imagery in an automated way. So we're looking at vegetation changes and soil topography changes, just on a very fine scale, and colour changes, to see what we can pick out. The whole approach means that we can scale this monitoring massively, reduce disturbance, but also lead to these standardised repeatable surveys that you can do on a regular basis. So a few things still to come to this platform. We're going to integrate some survey planning capabilities for drone surveys, but also with the ground surveys as well. Just collate all that relevant information you might need, like access points, tide times, road operators, just have it in a one-stop shop. We've got our first full season of data capture coming up next spring. We've got our 5 rarity sites given to us by NatureSmart and NCS that we're going to go and get secure imagery. Everywhere I'll come up with standardisation and best practice documents for data collection so that everybody can get on the same page in terms of what's needed, and they'll be able to fully integrate that to our platforms that like all organisations can access it. We're going to be collating other data layers like climate and sea temperature, wind farm locations, anything that will help give that holistic overview of a colony health and give you reasons as to why a colony number might be fluctuating over time. Related to that, we get national colony and burrow level analytics, statistics, and we'll fully trial that for detection and we'll see how that's working for ecologists as well. So obviously this isn't necessarily just about counting seabirds, this technology, but it's about the wider marine ecosystem and how technology can help protect it. So you might know from this new biodiversity structure that's been released that there's a rather ambitious target being nature positive by 2030. Whatever that means, who knows what that means. But the only way to get to that point is through better planning and better collaboration, and that tends to be enabled through technology such as this, these sharing platforms, data sharing, so that this information can be turned into quick decision making with policymakers and economic planning as well. And maybe some of the issues we've seen in the news around certain wind farms that we won't name might be better foreseen had they had better access to high quality geospatial data and mapping like this. So to sum up, traditional seabed monitoring is quite slow, very manual, but by using digital tools like drones, AI, geospatial analysis, we can really transform this process and make it faster, cheaper, scalable, and far less disruptive. And for gannets, this means near instant population counts during an epidemic like bird flu. And for puffins, it means moving towards standardization, large-scale solutions for burrow monitoring without having to round out thousands of goals. So digital ecology is a wonderful practical solution to help us respond faster, work smarter, and make more decisions for nature.